This is TechSNAP, episode 406, recorded June 23rd, 2019. Hello and welcome to TechSNAP, Jupiter Broadcasting Systems, Network, and Administration podcast. My name is Wes, and once again, I'm joined by Jim.
What's up, everybody?
As we sit down to record this episode, there's been plenty of security news this week, and one story we couldn't ignore was, well, a kernel panic in the Linux kernel, and that is the SAC panic vulnerability. There's been a lot of coverage, and some of that is screaming from the hilltops, and others are, kind of saying, there's not much to worry about here. I thought we could sit together, especially since, Jim, you administer a fair number of Linux boxes.
Just a few.
Maybe we could hash out what's going on here together, and how much do we need to worry?
Well, Wes, like most things, this is nothing new. Everything that has happened before will happen again and vice versa.
Right.
This is the ping of death all over again 20 years later. Back in the late 90s, 97, 98, there was a vulnerability in pretty much every networked operating system because they all came from the same original TCP stack code. It's called the ping of death. And the way the ping of death worked was there was an unchecked buffer in the TCP stack. And if you sent a ping with more than 65,535 bytes in the buffer, it would overflow, smash the stack, and do one of two things. Most frequently, it would just panic the kernel or blue screen your Windows machine, however you want to call it. But in theory, if you crafted that packet maliciously enough and knew enough about the target system, like with all buffer flow attacks, you could potentially execute arbitrary code remotely. SAC panic, it's the ping of death all over again. It's not quite the same. It's not just a simple buffer overflow from having, too large of a payload in a ping, but it works the same way in that you can eventually overflow a buffer and cause the system to immediately crash. With SAC, the SAC protocol itself is it's called a selective ACK. So normally with TCP traffic, we're probably all familiar with your basic TCP conversation. You have a send packet and you have an ACK packet, and ACK is short for acknowledgement. You tell the other side, hey, I received these packets that you sent me.
Right. And this is all about, it's the transmission control protocol, and you're trying to acknowledge things because it's not just UDP, right? We actually want to make sure that packets reach the other side.
Right. This is not UDP at all. And you're exactly correct. This is about controlling the transmission. So when your receiving side sends these ACK packets, these acknowledgments, it lets the source side know, hey, the other side got all the stuff that I sent it, so we're good. If it doesn't receive an ACK on any of the packets that it sent, then it knows it needs to send them again. Now, selective ACK allows the system on the other side to send a selective acknowledgement of what packets it did or didn't receive in a way that it makes things a little bit snappier. With the original just send and ACK, basically, if you lost a packet from a cluster of packets that wasn't all the way on the leading edge of it, you would end up having to send, a whole bunch of back and forth figuring out exactly what had been lost before you could resend it and go along your way. So selective ACK is a way to just say, oh, hey, I'm missing this one packet in the sequence that you sent me. And much like the original ping of death, it's vulnerable to a maliciously crafted series of SACs that can overflow a buffer on the system that was doing the sending in the first place and cause it to crash.
Yeah, I found that particularly interesting about this vulnerability is, selective acknowledgement, it's not new. The RFC dates from around 1996. And when you look at the vulnerability advisory, in this case coming out of Netflix, you'll see it affects kernel versions 2.6.29 and above. And, well, if you know anything about kernel versions, that's ancient.
The word is antediluvian.
Yes, that is perfect. And basically, this is just a flaw, an oversight, a miscalculation or lack of calculation in the Linux TCP stack. It's nothing inherent to the protocol. And in fact, we should be clear, there are multiple CVEs going on this week. SAC panic is the worst because it, actually panics the kernel. But both Linux and FreeBSD have several other related vulnerabilities.
Well, yeah, and I need to correct you a little bit, Wes. It's not just a Linux problem. It's a Linux and BSD problem. And the reason for that is Linux and BSD still share a common ancestor for their TCP stack. It does not affect Windows because although Windows originally shared TCP stack code with the the BSD code that we all started speaking TCP from, eventually Microsoft succumbed to their own not invented here syndrome and rewrote the stack from scratch. So Microsoft now has a completely diverged TCP stack written only according to standard, where Linux and BSD still share a lot of common code. So as long as you brought up those other two CVEs, Wes, they both also revolve around the same basic problem, with the SAC protocol. Well, neither one of them will allow to crash the system or to execute arbitrary remote code. Basically, they amount to annoying the other system really badly, forcing them to do a lot of unnecessary CPU work that can slow things down. One of them is purely about the SAC code. The other one, and less severe, the other one also requires a really low MSS setting. But at the end of the day, those are annoyances that chew up some extra time, so they're to some degree a denial of service, but they're not just the immediate, bring your system to a crashing halt that SAC panic is. After all, the panic in SAC panic, it literally means kernel panic.
Now, there's been some confusion around just who's affected, right? On the surface, if you've got like an internet-facing Linux box, you might be at risk, especially since SAC is enabled by default on many distros, but it's not really that simple, is it, Jim?
Yes and no. I would argue that it's even simpler than that. If you're one of those folks who doesn't apply system updates, then you're vulnerable. If you're one of those folks who are applying system updates on, a regular, predictable, well-scheduled basis, then it's already fixed for you because you've already applied those updates. You may need to reboot to get the new kernel, but that's about it.
Yeah, that's right. Always good advice.
But, to be a little less snarky, it kind of boils down to almost any Linux user prior to patching would have been vulnerable to this. Newer versions of FreeBSD who were not using some Netflix-specific code, I understand, were not vulnerable to SAC panic. But I'm not as active with FreeBSD as I was once, so I'm really just kind of going from some comments that I've seen on that.
Right. As always, check with your particular vendor to find out if you're affected. As an example of that, AWS put out some security bulletins as well because network load balancers, but not other types of load balancers, were affected. So as always, with particular vulnerabilities, go check everything you're running. We'll have links at techsnap.system/406 to some various vendor pages, and you can go see, of course, Ubuntu, Debian, Red Hat. They've already got patches out and available.
Yeah, and if for some reason you're on a system that you cannot patch the kernel, cannot get a newer kernel, whatever, you should really consider what led you down that path and try to figure out a way to fix that. But B, you can mitigate this simply by disabling SAC itself. It can have an impact on how much CPU time and network overhead is involved when you do have sketchy network sessions where a bunch of arbitrary packets get dropped, but that's probably not going to be a really big deal for most folks. And, it's a simple syscontrol command or edit of one line in syscontrol.conf away for Linux folks. The other thing that I think is probably worth mentioning here that really highlights the differences between, when this happened with the ping of death in 1997 and, happening with the SAC panic now in 2019. As I mentioned earlier, most folks they're already done with this. This vulnerability got disclosed. It was patched. The patches were made available and went out, all within a day or two. And it's pretty much a done deal for most folks out there, unless you're specifically refusing to patch your system. This is in pretty sharp contrast to the ping of death back in 1997. The internet was still full of machines that could be taken offline with one single ping, in 2000, 2001. People were going years not patching internet-facing systems.
Right. You would hear stories of people jumping into IRC rooms and just, sending out packets and seeing how many people they could, crash their systems and get them to log out. And that doesn't really happen to the same extent today.
And if it does, then you're just helping to prove my point. Stop doing that. Patch your systems. Life will be better.
Yes, in another instance of listen to Jim and just apply your patches, this one from the browser department, and actually it was 2 0 days. I thought this story was particularly interesting just because A, your browser is the program you use to reach out to the internet, and while you may mostly visit untrusted sites, It's an inherently risky proposition. And of course, browsers go to great lengths. We have a lot of sandboxing technology that's in use. Even so, as we'll talk about and with this vulnerability, it's dangerous and you need to stay up to date. Most often, you see attacks made against just large swaths of users, low-hanging fruit. These vulnerabilities were reported by Coinbase, and they weren't after Coinbase users, no. They're after Coinbase employees.
Yeah, this was a really cool story because, we're not just talking about script kiddie stuff or botnets or, trying to send some spam. We're talking about a real talented professional APT hitting a very high profile target. And they burned 2 0 days at once doing it. You don't see that very frequently. A single 0-day vulnerability, one that nobody has talked about or disclosed or patched yet. We're talking about roughly a 6-figure value on that just to sell that vulnerability on the open market. You can get 6 figures for it. So if you burn 1, let alone 2 of those in an attack rather than selling it, you're really trying to get some serious dollars out of that. And this attack versus Coinbase, whoever the attacker was, they chained together 1 0-day that would allow remote code execution in Firefox, and another 0-day vulnerability that would allow privilege escalation and sandbox escape. So that, normally if you get remote code execution in a Firefox browser or in Chrome, it doesn't buy you a whole lot by itself. Yes, you can execute arbitrary code, but you're in an extremely neutered process that the system it's in does not trust at all. So you can do something obnoxious like, maybe try to spawn some pop-ups, or you can do, network denial of service attacks using that code, trying to, talk elsewhere to arbitrary servers maybe. But you can't do much from there.
Right. You could use resources, but you're not going to go steal secrets from a machine.
Yeah, but this was 2 different 0 days. Like I said, one allows you to execute the code and the other allows the code to escape the sandbox and, actually run code on the underlying machine itself. Now, the idea here was that whoever this attacker was, they were trying to get inside Coinbase's network and, potentially compromise the crap out of them and get some serious, serious money. But mad props to Coinbase. They detected the attack. As far as we can tell, nobody actually got owned, and they pulled the malware apart, figured out what it was doing, reported the whole thing, and now both of those 0 days are completely burned. So our unnamed attackers are probably out about $250,000, not even counting the time that they spent, trying to stage the attack itself. It's a pretty cool story.
Yeah, as always, it leaves you with more questions than answers because we don't really know who perpetrated this attack, and we don't really know how they found these 0 days because there actually had been some bugs filed in Mozilla's portal, although the lay public does not have access to that. So perhaps they discovered it on their own or had some insider information. Either way, you can see how Coinbase's vast storage of all kinds of different cryptocurrencies, well, it's a tempting target.
So this is not the first really audacious attack against a high-profile digital currency exchange we've seen. Back in 2011, Mt. Gox got breached, and an attacker managed to do, I'm not even sure that the Mt. Gox attacker entirely knew what they were doing, because they actually managed to destroy a little over 2,600 Bitcoins by sending them to invalid addresses, where you would think that they could have found something better to do with that. But the transactions that they actually did successfully complete in the Mt. Gox attack, they moved more than $8,750,000 worth of Bitcoin. This affected the entire, Bitcoin ask price. It was an enormous deal. And presumably, that's kind of the inspiration for the attackers on Coinbase this time, because in a lot of ways, Coinbase operates a very similar place in the digital currency ecosystem in 2019 as Mt. Gox did back in 2011. There's not a whole lot of folks who are moving a lot of digital currency around that aren't touching Coinbase in some way.
I think that made it especially interesting to see some of the security analysis done by the Coinbase team, and hopefully that's reassuring to some of their customers.
Mt. Gox back in the day, it was to a large extent, it was the old image that all of us, in the Linux world are trying to break free from of, the guy in mom's basement eating chicken tenders at 3 a.m. There's basically just kind of one guy running it, and it was a pretty Mickey Mouse show.
The internet Wild West.
Yeah, Coinbase is clearly taking things a lot more seriously. Their security is obviously no joke. To catch and entirely analyze and report 2 0 days burned in tandem like that, that's a big deal. Not many people would be able to say, yeah, if our company got targeted that way, we would absolutely, catch an attack like that in the making and destroy it and burn it for the rest of the world, all in a week. And, Wes, you said earlier that this raises a lot of questions. Honestly, the only question I have at this point is, I wish I knew a Twitter account for the attackers just so I knew where to send the snarky, sarcastic GIFs.
Well, let's continue just a little farther down the security news of the week. And this is a follow-up on a story the TechSNAP program has actually been following for years. Some of our audience may be familiar or at least remember the name Rowhammer. This week we saw a particularly distressing update in a new vulnerability known as Rambleed.
Yeah, Rambleed basically is Rowhammer. It's just it's more of a read version than a write version. What it boils down to is if you can control a lot of the area of RAM physically wrapped around some protected RAM that your child process doesn't have access to, you can manipulate it in such a way as to give you hints and eventually disclose the actual contents of that protected memory that you're not supposed to know anything about. You're not supposed to know what's in it. You're not supposed to be able to read or write to it. But with Rambleed, you can kind of sniff around the edges. It's almost like the old TV trick where the kid goes up to the parent's door and puts the water glass to the door and their ear to the glass. You get around that barrier. And one of the nastier things about Rambleed is when Rowhammer first debuted back in 2014. A lot of the answer there was, oh, well, as long as you have ECC RAM, you're fine. You're immune to Rowhammer, which was sort of true, sort of not true. Nobody quite knew how to work around ECC with Rowhammer yet at that point.
Right. And the idea was with Rowhammer, you hammered against memory and were able to introduce bit flips basically because of some of the physical properties underlying the RAM.
Right. Whereas with Rambleed, you can gain information about protected memory by repeatedly writing in calculated patterns to portions of memory you do control that are physically adjacent, and you can eventually gain some clues about the contents of that physically adjacent RAM you don't have access to. And ECC RAM is not a mitigation versus Rambleed.
Now, the researchers don't suspect that this is currently in use in the wild, but they do have a great paper out. We'll have that linked in the show notes, of course. And if you're interested, I really do recommend reading it. This has been sort of an interesting story to follow because right now this is just a flaw in a lot of the RAM that is used in the industry. And while it hasn't been used, it's not crippling everyday computing, I suspect that as this research continues, we're probably going to see this in a similar targeted attack like we just talked about with Coinbase.
I mean, honestly, there's no way we're not going to see it because the researchers demonstrated in a proof of concept. It took them some time to do it, but they demonstrated an attack against OpenSSH and used Rambleed to leak a 2048-bit RSA key. And if you can get SSH keys, well, you've literally got the keys to the castle. That's about all that we really need to say about Rambleed itself, but I do think that we'd be missing a beat if we didn't notice that these days more and more we're seeing a lot of hardware hacking. Rambleed and Rowhammer and the speculative execution vulnerabilities, Spectre and Meltdown that we've seen targeting, both major families of x86 64 CPUs. We're going to continue seeing a lot of this where we've gotten to the point that InfoSec is nasty enough that it's literally exploiting the properties of physics itself against the hardware that we use. And that's something we're not going to be able to just conveniently ignore anymore.
Right. We can offer software mitigations, but fundamentally this is a problem with the hardware and it won't get fixed till that's fixed. And it's something everyone, from users to developers, needs to be aware of. All right. Well, that's far too much distressing security news. let's finish the episode up by talking about something exciting. And, well, if you've listened to TechSNAP, you probably know. Let's talk about ZFS. Jim, you had a great article out in ours this week talking about all the updates that have been happening for ZFS on Linux. And boy, it's a great time to be a ZFS on Linux user.
Yeah, there's a lot of stuff that just dropped last month with 0.8. OpenZFS as a project, it follows semantic versioning, which means when you see an update like, 0.7.5, 0.7.6, or whatever, you're only looking at bug fixes. When you see 0.7 to 0.8, you're going to see a whole bunch of, important new features. And 0.8 in particular was a huge release with some things that a lot of people have been looking forward to with great anticipation, myself among them. We've got native encryption on ZFS, much as you've always been able to do inline compression. Within ZFS itself, you can now do inline native encryption. You no longer have to rely on an external application like Lux or Jelly on FreeBSD. You can just tell ZFS, hey, I want this data set or this Z file to be encrypted and manage it all internally.
Right. Before, you had to do that at a separate layer with other tools, and then you just sort of gave ZFS these things, these block devices that were encrypted underneath, right? And now ZFS knows about everything that's going on.
Exactly. And, don't get me wrong, it was certainly possible. It still is perfectly possible to do Lux encryption either above or below the ZFS layer, or, use Jelly that way if you're on FreeBSD. But it produced some real issues doing that. First, you had to decide, do I want my encryption layer below ZFS layer? Do I want to feed ZFS already encrypted disks, or do I want to do it above the ZFS layer? Do I want to present, some Z-vols to Lux or Jelly and, build an encrypted file system on top of that? Either way had some real drawbacks. You have some performance implications either way because, now you've got multiple layers instead of one. But more concerningly, you can have issues with timing, getting things mounted. When you're first booting the system, does everything become available in the right order? So what most folks have done with Lux or Jelly, either one, is they've used that as the basis layer. And they create an encrypted block device using Lux or Jelly and feed that block device to ZFS. ZFS doesn't actually know that the block device beneath it is encrypted or not. Now, the nice thing about this is that it means that ZFS compression still works. Because ZFS is compressing the uncompressed data, then you actually will use less space on the underlying encrypted block device. However, it also means that now, instead of feeding ZFS actual disks and allowing ZFS to have direct control over when, where, and how blocks get written so that it can minimize the possibility for corruption and loss of data as much as possible. Now you're feeding it this software block device. It's going to be making a lot of decisions that ZFS doesn't know about. Now, if you do it the other way around, which is what I would typically recommend, say you feed, Z-vols running on ZFS to Jelly or to Lux, now you have the opposite problem. Now, although you can guarantee the stability and the, lack of corruption in your data because ZFS has access to the direct real devices, now ZFS compression won't work because all ZFS is seeing is this already encrypted thing, and you can't compress encrypted data.
Of course. So it's another case where just by combining those things in one code base, you can share that information, you have access to it, and you can get both benefits.
Absolutely. I mean, it's just another case of you can have a jar of peanut butter and you can have some chocolate, but if you don't put one inside the other and make one single thing out of it, it's just not a Reese's cup. But, potentially even more exciting than being able to get all the benefits of compression and encryption and reliability all at once. And one of the things that I really, really love about this project is it includes something called raw send. Now, if you're not familiar with ZFS replication, you absolutely should be, because there is no more efficient way to get data from A to B, even over a pipe that doesn't have great latency or doesn't have great bandwidth. Replication is amazing. Again, you would have a problem before if you had Jelly or Lux underneath your ZFS layer, like what most people were doing. Well, now if you use ZFS replication, you end up with an unencrypted copy of your data on the remote end, which is probably not what you want. Also with replication, up until raw send, if you had ZFS compression turned on, it would decompress the data from its condition on disk, send it over decompressed, and then either recompress it or not as, the properties of the target pool required on the other side. With raw send, you actually send the data on disk exactly as it is.
No extra processing or complicated decisions to make. It just gets streamed out over the wire.
Yeah, that means that if it's compressed, it stays compressed. You're not decompressing it, sending it, and recompressing it on the other end. It also means if it's encrypted, it remains encrypted. And now here's the killer feature. The system on the remote end doesn't have to have the key to decrypt it. So you can replicate a file system with data on it that you need backed up to a third party like rsync.net or somebody else that you don't entirely trust, and you don't want them to have access to the actual data. So they're now serving as a perfectly valid backup target, but they don't have access to the actual data. And that's huge.
Wow, that is an important update, and might be reason enough just to go get all the greatest and latest updates in ZFS on Linux. But wait, there's more. Another feature that caught my eye was device removal. And as you write, Jim, one of the most common complaints about ZFS, especially for hobbyists, people who are using it maybe for some stuff at home or just experimenting it as a backup target. Well, once you've added something to a ZFS pool, you can't undo it. You can't really remove it. So you can get into some complicated scenarios. And if maybe you don't have the right number of backups, or you're just experimenting, things can go wrong quickly. And in the past, there wasn't a whole lot you could do about that besides recreating everything. But beginning with 0.8.0, device removal is possible in a limited number of scenarios with a new zpool remove command. I wanted to ask you about this because that sounds nice. I could imagine a scenario where maybe you ran the wrong command, you accidentally added a drive to a pool you didn't mean to, or didn't quite get it configured correctly. In the past, I've always thought, just be careful. It sounds like this could be useful, but it's no substitute for really understanding what's going on with your file system.
Yeah, that's true, Wes. I kind of have a love-hate relationship with the new zpool remove command. Matt Ahrens, who is, don't get me wrong, absolutely the authority on ZFS, being its original father as well as one of the most prolific developers now, he feels a lot better about the command than I do, but the way that it works is it actually remaps blocks that are on the device that you remove from the pool to a new location where they exist after being moved, and then the device, can be disconnected and is no longer part of the pool. The problem is, this works kind of like if you're familiar with DNS administration with bind, it's almost like a CNAME record. So what's going to happen if you had a file stored on the disk that you removed? After you remove the disk, those blocks get migrated to disks which are going to stay on the pool, and there's a table that sits in RAM, and that table says to an application that asks for a block that should be on the removed device, it says, no, actually, yes, I can give you that block, but here's where you need to go to get it. So you've got this lookup table, you've got an extra operation there. You're also going to eat about, I believe it's 50 megs of RAM for every gig of data that was on a removed device. So I don't really find that all that trivial. It feels to me like you've introduced some unnecessary complexity in your pool that's going to be with you for a while. Now, if it's literally just a case of, I added a disk, I added 2 disks individually, and I meant to add them as a mirror, something like that, by all means, you don't need to destroy that pool. You can just use the remove command right away, get them out of there. There won't really be any lookup table for anything but a few metadata blocks in those devices that you added and just as quickly removed. On the other hand, I feel like a lot of ZFS users are going to look at this and they're going to think, okay, well, this will be fine. I don't like this VDEV that I've got. I want to add a new VDEV, and then I just want to go ahead and remove the old one, and ZFS will go ahead and move those terabytes worth of data over to the new, device, and it'll all be fine. And yes, in most cases, ZFS will do that, but you're going to be left with this giant lookup table that's you're stuck with it forever. I don't think that's a good idea. Also, zpool remove won't work at all in some circumstances. You cannot remove a RAID Z VDEV at all. You're just stuck with that.
Oh, interesting.
You can remove single disks and you can remove mirrors, and that's it.
So I see there are a number of complications. It's not magic undo for ZFS. It might be useful in some limited scenarios, but you still need to understand what's going on, and you should. Your data is important.
And now there might actually even be a better way now, using another one of 0.8's new features to, guard against your own screw-ups when you start messing around with the structure of the pool. Another new feature that got introduced is called ZFS pool checkpoints. Now, what a snapshot does for an individual data set or ZVol, a checkpoint does for your entire pool. And when the feature is introduced, they're mostly talking about it as being, kind of a mollyguard for before you go to do a zpool upgrade. When new features are introduced that require changes to on-disk storage.
Right.
If you're worried about something potentially going wrong, well, you can first zpool checkpoint the pool and then do your upgrade. And if something goes badly, then you can roll back to that checkpoint you took just before the potentially dangerous operation. Now, I haven't actually confirmed this, but it occurs to me that you ought to be able to do the same thing before you do any device changes to a pool. Because the whole point of the zpool checkpoint is it preserves the entire state of the whole pool. I really need to reach out to Matt and the team and make sure this is the case, but it looks to me like you should be able to instead just make that a part of your practice. Before you mess around with the topology of your pool, meaning add new disks or anything like that, go ahead and take a checkpoint. Then if you discover that you bobbled the command and you meant to add a mirror and instead you added 2 individual disks, now instead of having to mess with zpool remove, you should be able to just roll back to your checkpoint and then do it the way that you meant to do it. And now you don't have any kind of a lookup table or, any other stuff left at all. It's just like you did it right the first time.
Why not take advantage of the amazing features of ZFS? I like that.
Absolutely. And, the other thing that I should mention, which is potentially a really big deal about zpool checkpoints, one of the things that currently there really isn't any good way to recover from, if you accidentally destroy a data set or a ZVol or snapshots that you didn't intend to.
Oh gosh, and that's a worst case scenario sometimes.
Yeah, that's kind of your nuclear scenario. At that point, your only hope is that you've been, as you should, replicating to another pool and you can restore from there. But with zpool checkpoint, you could, again, get in the habit of saying, okay, well, before I destroy a bunch of stuff, let me go ahead and set a checkpoint. And then if it turns out, oh, no, I destroyed the wrong thing, that was a mistake, I need to be able to undo that. Well, you can also use a zpool checkpoint rollback to undo the destruction of data sets or ZVols or snapshots. Now, the last thing that I do want to mention about the zpool checkpoints, I see a lot of people saying, oh, okay, or I can also undo it if I destroy my zpool this way, right? Now, there's good news and there's bad news. The bad news is, no, you can't undo zpool destroy with a zpool checkpoint because the whole pool's gone. You destroyed it. There is no checkpoint.
Right, that's a subset of the pool.
The good news is zpool destroy is not actually a destructive operation. If you haven't done anything else with the disks or with the partitions to write over that data, you can actually just feed the -D argument to zpool import, and you can import a previously destroyed pool, and nothing was lost.
And capital D, you just have to manually specify the disks? Is that what's going on there?
No, just like any other import operation, zpool import will automatically scan all the places that it knows of to look for block devices, which by default is going to include, the dev directory with like the raw disk names, dev SDA, dev SDB, that kind of thing. By default, it will also include dev disk by ID on Linux systems, which is where you find, your symlinks to the raw device names by WWN ID on the drive or by their serial ATA name and serial number. Without the -D argument, zpool import will automatically scan all the disks, and if it finds a pool which has been exported, or even one that has not been exported, if you use a force argument, you can forcibly import it, but it will ignore anything that's actually been destroyed. Feeding it the -G just tells it, yes, I also want you to include discovery of any disks that have destroyed pools on them, and treat it as though that pool was never destroyed at all. If you did need to actually feed the import, the actual place to find those disks. Like if they were block devices that didn't exist, in dev or in dev disk by ID, but were, I don't know, maybe they were sparse files that you created in your user directory or something. You can use the -d argument and tell it where to actually look for those individual block devices. But normally, you shouldn't need to do that.
All right, well, there's another big update we should talk about. And dear audience member, you might be familiar with it if you're someone who uses both ZFS and has solid-state disks, because for a long time, ZFS on Linux has lacked support for trim. That's no longer the case.
Yeah, if you're not familiar with trim, basically solid-state disks need to be actively told what blocks are no longer necessary and they can get rid of. That's what trim does in a nutshell. Without trim, your performance ends up degrading on a solid-state disk over time. Over the course of several years, you can end up down to, roughly a third of your original performance on, most decent models of solid-state drive.
And that's just a consequence of the complicated nature of how solid-state disks work, right? You need a little extra help to make sure everything keeps running and their firmware can do all the right optimizations.
Yeah, exactly. Now, on the one hand, if you're just comparing SSDs to Rust, you might, and as I have said for years, well, even if the performance does get down to a third of what it was originally, depending on whether you're talking about throughput or, latency and IOPS, the original performance was somewhere between, 5 to 6 times more than a really fast Rust disk, or, as much as, 10,000 times the performance of the Rust. So who cares if it's down to a third? I've taken that position for a long time, but now that we have trim support, I no longer have to. Trim just works with ZFS in 0.8. You can set the auto trim pool property to have it just done automatically in real time as blocks become available, no longer needed. You can notify the SSD right then. If you have a very performance sensitive system, you might also choose to leave auto trim off, but just set a cron job to do zpool trim manually in off hours and let it do that trim maintenance when you're not looking for maximum performance.
I love this update, both for the obvious performance improvements, but also for how well it integrates in. And having done a little bit of ZFS work this week, you can check out the most recent episode of Linux Unplugged if you want to hear more about our adventures converting a free NAS box over to using ZFS on Linux. But it's just another reminder to me that administering a ZFS system is so great, right? You can set the auto trim pool property if you want, and it just fits in. It's a new feature, but it's not a burden on the administrator, and it's easy to use.
Wes, one last note on ZFS before we close out that topic for the week. In the article that I wrote on Ars Technica about the 0.8 and 0.8.1 releases, I kind of misspoke myself a little bit, and I rubbed some BSD folks the wrong way. One of the other cool things that has happened over the last year is that OpenZFS across its many platforms, it's getting integrated a lot more tightly. We're moving forward to a single repository and, having port code underneath that repository handling, individual platform specific code required to make things run on FreeBSD or Linux or what have you. And moving forward, everything is just going to be OpenZFS. You're not going to have ZFS on FreeBSD. You're not going to have, Delphix ZFS on Illumos. You're not going to have ZFS on Linux. It's all going to be OpenZFS on whatever platform it runs on. Now, in recent years, an awful lot of the development work has been done originally by Linux developers on the Linux platform, and so it's moved out of ZFS Linux to other platforms rather than in the past, almost everything got done on Illumos, and, everybody ported the features down from there. As a result of that, the ZFS on Linux GitHub repo is going to end up becoming the master repository, and it's going to host both the main code for OpenZFS and code for platform-specific stuff for FreeBSD, for Illumos, and what have you. I misspoke myself a little bit accidentally on Ars. I will admit I've gotten annoyed in the past at zealots of other platforms crowing for no good reason that ZFS on Linux is not real ZFS, and I might have let that bleed through a little bit. The real answer is ZFS everywhere is real ZFS. ZFS on Linux is OpenZFS. ZFS on FreeBSD, same. On Illumos, same. On Mac OS, OpenZFS on OS X. same. It's all ZFS. It's all real boys. There's no Pinocchios here. And I'm really, really happy about the move that the project is making to tighten everything across all platforms and make it one big family.
I love it. It does seem like to be a sort of graduation of sorts as things have migrated out of the Illumos tree to its own independent project up on GitHub with lots of nice new stuff, like continuous integration, testing, and upfront support for all kinds of platforms. And to me, it just is another great reminder. OpenZFS is the file system for your data, and it's what you should be using.
Believe it or not, we even have an alpha project for ZFS on Windows. Now, that one is very much alpha.
Say what, Jim?
Yes, that one is very much alpha, maybe even pre-alpha, honestly. But one of my subscribers in RZFS on Reddit has been talking about that a little bit recently. He is working on it. He has a project available. You can actually install and you can create a file system. It is not at the point yet where you should actually rely on it. Let me be very clear about that. But it's really exciting. We actually even have progress going. Maybe one day Windows gets to be a real boy too. Or, maybe it goes the other way and Microsoft finally realizes that Apple had the right idea. They get rid of the Windows kernel and, just rebase their UI and platform compatibility layers on top of Linux, and we can just go from there.
Hey, they've got that new WSL2 VM, so they're getting closer.
Maybe one day Windows subsystem for Linux means the subsystem on Linux that runs Windows code.
We can hope. If you'd like to learn more about all the great updates coming to OpenZFS, we'll have a link to Jim's article and everything else we've talked about over at techsnap.systems/406. There, you can also find ways to get in touch with us and find our whole back catalog. You can also head on over to jupiterbroadcasting.com if you'd like to find all the other fine shows on the Jupiter Broadcasting Network, including such classics as Linux Unplugged. And if you haven't had a chance, go check out BSD now. It's sounding better than ever. I'd also like to take a moment to point you over to Linux Academy. They make TechSNAP possible, and we're very grateful they do. It also turns out, they're hiring. It's not only a great place to work, but you also get to work on a mission helping students learn. So whether you're interested in becoming a training architect, and boy, are they hiring for things like AWS, Azure, DevOps, databases, or even machine learning or Python development. All are great opportunities, remote work, and you get to spend your time making resources for people to learn about what you're interested in. It's really a great opportunity. Linux Academy is also hiring for engineering positions. So if you're an Angular or Node.js or Ruby on Rails developer, come join on, take a look at the opportunities. We'll have that linked as well. They're remote full-time positions, great benefits, and you get to work on building a platform to help people learn. That's going to do it for today's episode of TechSNAP. Thank you so much for joining us. If you can't wait until the next episode, don't worry. We're both on Twitter. I'm at Wes Payne, and Jim, you're?
At JRSSNet.
And you can find the whole network at Jupiter Signal. Thanks so much. We'll see you next time.